Hello, everybody. I think we've got everything going here, and we'll be starting right now. We're going to continue our discussion of aldehydes and ketones. And today we're going to start looking at reactions of said species. And we're going to look at two major approaches of how aldehydes and ketones react. The main approach we've seen previously in chapter 15, and that is nucleophiles with their lone pairs being attracted to the carbonyl carbon because of its positive nature, and attack forming a new bond, and then pi breaking and becoming an oxide. And then in our next step, we were using HCl. I copied some examples from chapter 15. Where we used organolithium compounds like isobutyl lithium, attacking formaldehyde in this case. So we got a 1 carbon extension. There's the new carbon. And we have an oxide ion, which can become an alcohol. So a useful way to do a 1 carbon, what we call homologation, is to react with formaldehyde. Similar results are obtained with Grignard reagents. Grignard reagents having an anionic carbon that attacks a carbonyl carbon and makes an carbon-carbon bond. Here's our new propyl group. Here's the new bond. And you get an O-, which becomes OH. So all of this is review. In case you want to look at the mechanism, I copied it here too, but we're not going to go over that again. It's typically one of the students' favorite mechanisms because it's pretty straightforward. So we can make carbon-carbon bonds to aldehydes and ketones using Grignards and organolithium compounds. Next up, we're going to look at hydride. And hydride here is going to do what our organolithiums did previously. Normal hydride like lithium hydride or potassium hydride, those are typically used as bases. So let's even put a note about that right over here. KH, NaH are typically used as bases. They do not attack carbonyls. Instead of they, we'll say these H- hydride ions do not attack carbonyls. So there. Hydride attached to a boron is a more nucleophilic hydride. If you recall electronegativities, these anions are not as anionic, if that makes any sense. Boron's electronegativity is 2.0, sorry, H is 2.1. So if we're looking at a boron hydrogen bond, it's not as profoundly ionic as if hydrogen was attached to a metal. And to get these mechanisms started, we have to liberate the hydride ion. Why does this happen if there's not much of a difference in electronegativities? Well, we have boron with 4 bonds, and it has an anionic formal charge, and hydrogen being next door says, I'd rather have the electrons than you. I'm more electronegative, and it takes them away. And boron has no formal charge when we're done, and we have a hydride ion looking for anything positive to react with. In this case, we have an aldehyde it's reacting with. We could interchange this with borohydride with aluminum hydride. Aluminum hydride is typically more reactive. It's a more general hydride reactor, and it does more things. Sodium borohydride is more selective. We'll explain the use of that word more fully a little later. And just like when we attacked an aldehyde or a ketone with a Grignard or an organolithium, we generated an oxide ion in both cases, which we then neutralized using hydrochloric acid. And this is another way to make alcohols. Useful molecules, alcohols. So what was the overall outcome when we started with something that had a pi bond from carbon to oxygen? I'd like to point out a less electronegative carbon was bonded to a more electronegative oxygen, and that bond is gone. What did it get replaced with? It got replaced with a bond to a less electronegative hydrogen. We call this form of a reaction reduction. Reduction. And reductions are reactions that replace bonds with more electronegative atoms with bonds to less electronegative atoms. All right, get a little better color action on that one. And the reduction step happens right here. Now, this is not the first time we have explored reduction reactions. I would like to remind you that in Chapter 6, we first explored reduction reactions, and we used hydrogen and a transition metal catalyst. And these reactions were very fast. And we took this pi bond here and replaced both bonds to carbon, the pi bond between carbon and carbon, with a bond to hydrogen on both carbons. Both carbons got reduced. If you attempted to do the same reaction with an aldehyde or a ketone, you would meet with certain failure. You do not get a reaction. Why is this? Why do we get no reaction? It's a pi bond. It readily happened over here, and it's very reticent over here. Why? Well, the reason is hydrogen is a non-polar molecule. It tends to avoid polar molecules and tends to associate with non-polar molecules. So there is a repulsive nature to hydrogen coming close to the carbonyl. That is the main reason. This can easily be overcome by presenting the carbonyl with a high pressure of hydrogen, which would literally force them on top of each other. And this is achieved much more simply than you might think. You can actually do this reaction in a syringe where you load up your ketone in there and you put in hydrogen gas above it and some platinum metal, finely divided platinum metal. And then you put the syringe plunger, and you can even do it by hand and press them together. Pressing together shrinks the volume of the syringe, creating pressure. You can obtain close to 5 atmospheres with a good strong hand, and you can get the reduction to happen. So I need to see that you acknowledge pressure is needed to accomplish this reaction. The results are identical to the results at the top of the page. You get a new hydrogen on the carbonyl carbon. There it is. And unlike the top of the page, you get that bond At the exact same time, you get the new bond between oxygen and hydrogen. And on the top of the page, we did it in 2 separate steps. We put the hydrogen on the carbonyl first, and then we protonated the O- to put the hydrogen on the oxygen. So up here, we have a reaction that's it's a little cheaper if you're doing small scale. Down here, this is the way you would do it on a large scale, because even though platinum is a very expensive catalyst, you only have to buy it once because catalysts can be recycled and reused, and hydrogen is very cheap. So when they scale up things to industrial scales, they will find excuses to make this the method to reduce aldehydes or ketones. So there you go. Hydrides can reduce aldehydes and ketones. Moving along. We're going to do a reaction of the other type now, the one where the carbonyl is the reactive species on the oxygen instead of the carbon, and it's going to act like a nucleophile up here, and instead of this being an electrophile here initially. And this is a real life example down on the bottom of the page, but let's just look at this simple example up here. We're treating a ketone with hydrogen cyanide. I'd like to point out hydrogen cyanide is an incredibly toxic compound that's been misused in history. I will only have to mention something like Auschwitz to bring out the importance of how we should treat each other better. Hydrogen cyanide, useful in organic chemistry. You have to take extreme precautions when using any cyanides, as my Orgo 2 lab students will attest. And what happens here is you get what's called a cyanohydrin. Cyanohydrin. This is not the first time we've seen hydrin as a suffix. Recall. Halohydrins. Yes, different reaction entirely, but worth reviewing since hydrin is common to both. Halohydrins were made from alkenes. Let's just do a simple example. And if we reacted it with bromine in the presence of water, we call that bromine water. We got a halohydrin. And that was when we learned about Markovnikov, more electronegative O on the more substituted carbon, less electronegative halogen on the less substituted carbon. And hydrin was just this piece right here. Hydrin is alcohol. And as we see in our new example, we have a new alcohol. And cyano is fairly self-explanatory, just like halo was, except in our previous example, this was a vicinal halohydrin. And in our new example, it's not vicinal, it is, let's type it in here, geminal. Geminal, I believe, is a new word for us. Geminal comes from signs of the Aquarius. If you're a Gemini, you know you're named after the twin sign. So they both live on the same carbon is what geminal means. Okay, so we got a couple new words today. Cyanohydrin and geminal. I think you're going to like this mechanism as well. hydrogen cyanide. If you're curious and you're not required to memorize, pKa is in the realm of 10. If my memory serves, it's a little closer to 11, but we don't have to memorize that. So this equilibrium in this first reaction, what's misleading, it's not even drawn as an equilibrium, is it? But it is, but it vastly favors the reactants and not the products. This is an oxonium. If you remember, the pKa is -3. And we take the left acid minus the right acid. And we get a very unfavorable equilibrium. It means, this number means we need 10 to the power of 14 of these to get one of these. Remember, it's a log scale, 10s to the power of. Okay, so how can this reaction even work if such unfavorable equilibrium is established? Well, the answer is when you have a second reaction that makes a new sigma bond between the carbon here, the cyanide carbon, and this very reactive carbonyl. In fact, today's theme is to call that, yeah, it's today's theme. Talk about it all day. A protonated carbonyl is also known as an activated carbonyl. I think we're back to week 1 with this pen. I don't even know how that happened. It's not writing for me. That is pretty strange. Insert your own O there. We have an activated carbonyl, and it's going to be attacked readily with a strong nucleophile. We're going to see later another reason to activate a carbonyl would be to attack it with a poor nucleophile. That's coming up very soon. And this is a very favorable reaction. Any reaction that replaces pi with sigma in terms of potential energy is favorable. Just a quick little sketch of that. Got your potential energy diagram. Species with pi bonds tend to be higher potential energy. If you have pi, down here we have no pi. And that's a favorable reaction when it's exothermic like that. So we're drawing this activated carbonyl away from the unfavorable equilibrium and replacing it with a cyanohydrin. And every time you remove a molecule from equilibrium, you have to replace it in the equilibrium. So even unfavorable equilibria can be driven towards the unfavored side as long as you do something to remove one of the species from the equilibrium. And there you have it. There's an organism on this planet, not a very pleasant looking organism. It's called a millipede. It's an insect, and it sequesters using its diet benzaldehyde from things like almonds, apricots, apples, and cherries. And it also has cyanide sequestered safely. And what it does is it performs this very reaction here to create a cyanohydrin, and it stores it in a gland. And upon treatment, if the animal's presented with an event that it deems dangerous, then it will have a reverse reaction. It will open up that gland and cause the backwards reaction to happen, emitting a pleasant smelling almond odor in benzaldehyde and a very toxic chemical hydrogen cyanide. I would like to calm your nerves a little bit here. A millipede will not hurt you. The dosages of hydrogen cyanide are very small, but if you're another insect, they are approaching a lethal dose. So This animal knows how to protect itself. And let's see, is this a good spot to, I think this is a good spot to stop for our first break, and we'll pick up after the break with hydration of aldehydes and ketones, which is going to require activation. And I will see you in 5 minutes.